Ever wondered how AI models shrink from massive supercomputers to tiny phone apps without losing their smarts? It's all about quantization, a process that simplifies neural networks by reducing their precision. But here's the tricky part. When you compress a model, you need to optimize it so it still performs well. That's where the Hessian matrix comes in, a mathematical tool that helps find the best way to adjust model parameters. But calculating it directly is computationally expensive. So researchers use clever approximations. Let's break down how they do it. The key player here is the Fisher Information Matrix, FIM. Think of it as a roadmap that shows how sensitive a model's predictions are to changes in its parameters. Instead of computing the full Hessian, which is like a massive, complex puzzle, BRECQ uses FIM as a shortcut. But here's the catch, FIM isn't perfect. The method approximates it by focusing only on the diagonal elements, essentially, the most straightforward parts of the matrix. While this speeds things up, it ignores important relationships between parameters, leading to inaccuracies. Here's where things get interesting. The researchers discovered that BRECQ's approach of using squared gradients to estimate FIM's diagonal is flawed. Gradients measure how much a model's output changes with tiny parameter tweaks, but squaring them doesn't always capture the full picture. Instead, they found that divergence gradients, which measure how much a model's predictions change when you alter its inputs, provide a more accurate alternative. It's like switching from a blurry photo to a high-definition one. The details matter. But how do you balance accuracy with efficiency? The team developed improved approximations. For example, the rank 1 method assumes the FIM can be simplified into a single dominant pattern, while low-rank approximations capture multiple patterns without overwhelming the system. The most innovative approach, DPLR diagonal plus low rank, combines the best of both worlds. It's like using a hybrid car, mixing efficiency with power to get the job done better. These advancements aren't just academic, they're practical. By refining how we approximate complex matrices, we're making AI more efficient and accessible. Whether it's running on a smartphone or a robot, these techniques help models stay smart without sacrificing speed. Next time you use an AI app, remember, behind the scenes, math is working overtime to keep it fast, accurate, and tiny. What do you think? Will smaller AI models change the way we interact with technology? Let me know in the comments. Ever wonder how AI gets smarter without needing a supercomputer in your pocket? Let's break down a key discovery that's making neural networks more efficient without sacrificing performance. Imagine you're baking a cake, but instead of following a recipe, you're experimenting with different amounts of flour. Too little and it's a mess. Too much and it's dense and heavy. Researchers did something similar with AI data. They tested how different sample sizes affected two steps in the process, FIMA and reconstruction. FIMA. Think of it as the first pass, like mixing ingredients. More data helped, but the gains were modest. Then there's reconstruction, the real magic trick, where the model refines its understanding. This step really felt the difference. With 1,024 samples, it nailed the details, but even 128 samples gave decent results. It's like finding the perfect balance of ingredients. More isn't always better, but there's a sweet spot where everything clicks. Why does this matter? These techniques are the unsung heroes behind faster, lighter AI. Think about your phone's voice assistant or a streaming service's recommendations. By optimizing how data is sampled, we can build smarter systems without cranking up the computational power. It's like teaching a kid to ride a bike. With the right support, they'll go further faster. So next time you see an AI learning something new, remember, it's not just about raw power. It's about smart shortcuts, clever math, and knowing when to stop adding flour to the batter. Thanks for sticking with me. Drop a comment if you want to dive deeper into the numbers behind the magic. Stay curious, and I'll see you in the next video.